Hi, my name is Arha, and this is my Physics Lab 2. Here's the introduction. The purpose of this lab is to determine the effect of forces, specifically drag force and gravitational force, on an object with a parabolic trajectory. In order to do this, we analyze the system and surroundings in the tracker application. The system in this situation is the ball, and the surroundings are the air and the area around the ball. Here are the models used in this experiment. There are charts from Tracker and a GlowScript program that predicts the motion of the object with only gravitational force and a combination of gravitational and drag force. You can see the code above, and you can see some of the Tracker charts below. Here are some physics principles. The first principle that is used in this lab is the definition of net force, and this is by far the most important principle of this lab. The net force is the sum of all forces acting on the system, and in this lab, we look specifically at drag force and gravitational force. Other principles that are used in this lab are the momentum principle and the position update formula, which you can look at below. Here's the drag force model, which is really fundamental to this lab. The drag force is always acting on the opposite direction of motion, meaning that it has a component in the x and the y direction. And you can see that drag force is derived by the equation negative b times the speed times v hat. And b is a proportionality constant that's determined by my data. Here's the preview of the results. Gravity alone would cause the object to fall down at a much faster rate, and the x velocity would be constant. With the addition of drag force affects the x velocity, making the x velocity non-constant and causing the object to fall down at a much slower speed. Here are the models used in this experiment. You can see that the blue line is the original data, the red line is the line with gravity and drag included, and you can see that the yellow line is just with gravity, and with gravity alone, the object falls down at a much steeper slope, meaning that it falls down at a faster rate. You can see some of the drawings from GlowScript that also show the same situation, and you can see the GlowScript predictor that shows the ball and the motion and the drag force and the gravitational force. Here's the experiment. The procedure for this experiment was as follows. We threw a paper ball in the motion of a projectile. We used the tracker application using a calibration stick to find positions at different locations during the trajectory. After doing this, I made an experimental model on GlowScript to mimic the motion that was seen on tracker. The code for that is shown on the next slide. Here's the experiment code. You can see that the drag force formula is pointed at below, and the force of gravity vector is also pointed at. Fnet is the sum of both the gravity and the drag force. Then we use the position and velocity update formulas to update the position and velocity, and it's used again in the while loop. Here's the initial data. The ball's mass is 0.005, and then here's the position and velocity. And B was changed to find a model without drag force, since if B equals 0, then there is no drag force. Here's how I found B. To find the value of B, the drag force constant, I used my knowledge and the fundamental principles of physics to find drag force. Because F drag is defined by the equation above, we can use our knowledge of what net force is to rearrange the equation. And by doing so, I found my B, which was 0.01, which is accurate and brought me really accurate results. Here are the conclusions that we got. Some sources for error. There are several areas for error in this experiment that show the little tiny errors that we had in the graphs that were shown. Tracker is not as accurate as real life, and as a result, the velocity, acceleration, and position could be off, affecting the drag constant. There are other forces that we could have forgotten to take an account of, and there's infinitely many forces acting on an object from its surroundings, and as a result, this could also affect the data. Human errors, such as incorrectly clicking on the center of a mass, could cause the tracker application to cause an error and not accurately predict the motion. What if? Terminal velocity cannot be predicted from this experiment because there's sometimes no net force in the x direction, and other times there's no way to balance the net force. The only way that it could be predicted was if gravitational force was the only force acting on the system. An experiment that could be designed to find terminal velocity that's besides this one could be done where a ball was dropped straight down and air resistance and drag force was considered, and then terminal velocity could be determined. What does it mean? A projectile is launched with a horizontal velocity. It follows a curved path, and this curved path takes longer to reach the ground. The object will experience air resistance throughout its horizontal and vertical motion, and while the horizontal motion does not affect the time to fall, the overall drag force could slightly affect the vertical descent. And the straight down. When an object is dropped straight down, it only has a vertical component of motion. In essence, the projectile might take slightly longer to fall than an object dropped straight down due to the combined effect of air resistance on both horizontal and vertical components, as seen in the formulas shown.